Hi, this video is a follow-up of a previous video where we had considered different strategies to optimize a function on an open interval. Here we illustrate each strategy on the same problem. Consider the following problem. Find the minimum of f of x equals 8 over x plus 2x minus 7 on the open interval 0 infinity. Note that f is the rational function 8 over x plus the polynomial 2x minus 7. 8 over x is continuous for all numbers except 0, and 2x minus 7 is continuous for all numbers. Therefore, f is continuous for all numbers except 0. In particular, it is continuous on the open interval 0 infinity. The first three strategies will work only if f is continuous, so this is a pretty important property to verify if we're going to apply any of them. If we did not have continuity, then graphing the function f would probably be our only option. In addition, because f is the sum of a rational function and a polynomial, it is also differentiable everywhere except at 0. This means that any critical number will have a derivative that is 0, and there are no corners for the graph of this function. Now that we know that we can apply the previous strategies, we use this problem to test out each of them. To apply the first method, we need to find the critical numbers. Since f is differentiable, then there are no corners for this function, and we need to find all c in the interval 0 infinity such that f prime of c is 0. Among these critical numbers, we need to show that there is one where the function decreases for x less than c and increases for x greater than c. First of all, the derivative of f of x, written as 8x to the minus 1 plus 2x minus 7, is minus 8x to the minus 2 plus 2, or minus 8 over x squared plus 2. Setting this derivative to 0 gives two solutions, minus 2 and 2. You might want to pause the video to take a look at the details of the solution. Only x equals 2 is in the open interval 0 infinity, and this is the only candidate, or critical number, we have for a minimum. To see if the function increases or decreases on each side of 2, we do a sign chart of f prime. We put on an axis the bounds of our interval. Here there's only the lower bound 0 to put on the axis. And we also put our critical numbers. Here there's only one to add since only 2 lies within the interval. Above the x-axis, we indicate the function values for f prime. Because f prime of 2 is 0, we put 0 above 2. The sign of f prime can only change between its critical numbers. To decide what the sign of f prime is, we can use some test points. For example, 1 lies between 0 and 2, and f prime of 1 is minus 8 plus 2, which is minus 6, which is negative. So that means that f prime is negative for all values between 0 and 2. Above 2, we can use 4 as a test value, and we see that f prime of 4 is minus 8 over 16 plus 2, which is minus a half plus 2, so 3/2, which is positive. So that means that f prime is positive for all values above 2. We add all the previous information found in our sign chart. Notice the minus sign and the plus sign before and after 2 to indicate that f prime is negative before 2 and positive after 2. This means that the original function f is decreasing when x is less than 2. So notice the word dec on the sign chart, so dec for decreasing, and increasing when x is larger than 2. So notice the word inc on the sign chart. Therefore, there is a global minimum at x equals 2. Its value is f of 2, which is 8 over 2 plus 2 times 2 minus 7. So that's 4 plus 4 minus 7, so 8 minus 7, so 1. In the second method, we find all critical numbers and try to show that the function is concave up by showing that the second derivative is positive on the interval. We already know that 2 is a critical number and that f prime of 2 is 0. So now f prime prime of x is the derivative of the derivative minus 8 over x squared plus 2, which can be written as minus 8 over x squared, which can be written as minus 8 times x to the minus 2 plus 2, and the derivative is minus 8 times minus 2 times x to the minus 3 plus 0. If we write our second derivative using a positive power of x, we get 16 over x cubed. When x is in the interval 0 infinity, then x is positive and so is x cubed. Therefore, the second derivative 16, which is positive, over x cubed, which is positive, is also positive, and this means that f is concave up. Once again, we conclude that there's a minimum at x equals 2. In the third method, we show that f of x goes to infinity at both endpoints of the interval. As we approach 0 from the right, the limit of 8 over x plus 2x plus 7 is obtained by considering the limit of each term in the sum. 8 over x goes to infinity, since dividing 8 by numbers increasingly close to 0 gives numbers that are increasingly large, so 8 over x goes to infinity. 2x goes to 0, and 7 is constant. So overall, this is the limit of the form infinity plus 0 plus 7, and the limit is infinity. When x goes to infinity, 8 over x plus 2x plus 7 goes to 0, plus infinity plus 7, so infinity overall. Since at both endpoints the function goes to infinity and f is continuous, in between there's a global min. Because f is differentiable, it occurs where f prime of x is 0. And we already know that f prime of 2 is 0, so therefore at x equals 2, there's a global minimum. This last figure shows the graph of f and its minimum at x equals 2. We can see that the function, as expected, decreases before 2 and increases after 2, and that it is concave up. Furthermore, at 0 and infinity, the function goes to infinity. In particular, there's a vertical asymptote at x equals 0. Therefore, by graphing f, doing sign charts for f, f prime, and f prime prime, and identifying the asymptotes of f using appropriate limits, we could have come up with this graph to conclude that there's a minimum at x equals 2. So clearly, this would have been more work than what was required in the previous methods. Thanks for watching.